This is a Build a CubeSat challenge, the final project by Sachit Vasu and Nilesh Shinoju.
So this is our ConOps. It starts up in the off state, then moves on to the on state. Then from there, it goes on to the solar panels and the ADCS/IMU. And then it will go on to the camera where it will reinitiate 3 times if it fails. Then it will go to the after orbit stage where if it passes, it'll take pictures of the damaged area and the existing area. And it will analyze those images and upload them to the GitHub.
So our experimental setup will be like, we'll have our CubeSat will be attached to a tram-like railing system, and each cross of the railing system will be one orbit, and we'll model buildings and roads out of common objects, such as Legos, and toy cars.
So our battery pack on our CubeSat will be our main power source, and our solar panel is our secondary power source. The solar panel is just attached to the power bank to increase usage, and this is similar to a functioning orbiting CubeSat, which uses solar panels to be used in space. So our power budget, so the Raspberry Pi has different power requirements, and it requires 2.6 watts to operate. So our battery pack is around 10,000 milliamps. It outputs 3.7 volts, which converts to 37 watt hours of usage. In the end, this makes the battery pack last for around 14 hours, and assuming any unpredictable aspects such as extra CPU usage or other failures, it can give around 7 to 14 hours. The solar panel can give more usage.
Okay, so this is our ADCS. So this essentially determines the location where we're going to take images. So we use the IMU and we use sensors such as accelerometer, magnetometer, and gyroscope to determine, and we use RPY values to specifically determine our position.
So for the imaging, the camera will take images of the before and after the disaster, and the images will be moved into a folder, and it will run through the software subsystem and highlight the differences between both the pre-hurricane and post-hurricane pics. And the images with the highlights are updated into the folder and sent to the ground, which is the GitHub. And the image format is JPEG because JPEG has faster loading times and can scale the image to fit. And they're best for images which are photographs, unlike static or animated graphics. And the difference can now be seen and identified in the GitHub. So this is our link budget. So the equation is PRX equals PTX plus G minus L. So what this means is that we have the PRX, which is it calculates the strength of the signal on the receiver side, and the PTX is the power transmitter. The G and the L is the gain and the loss between both antennas during the transfer, and general values for the PRX, PTX, and the gain and the loss are the PTX is 13.01 decibel milliwatts. The gain and the loss is 2 decibels and 1 decibel. And the output, which is the PRX, would be 376 milliwatts, which is approximately 25.7 decibels.
Right, so this is our general overview of software. So we'll align ourselves by detecting which location has the highest pre-hurricane probability, and then we will take pictures every single time at that location, and then we'll send it to the ground station. So we'll use image analysis to determine to analyze our images. So we'll use an AI model to determine it, and these are some indicators. We'll use like flooded streets and intact buildings. Okay, this is our CAD model.
This is our current CAD model. The contents include the Raspberry Pi, which is the green item in the middle, the IMU, which is next to the Raspberry Pi, the small black item, the camera, which is the red item below everything, the casing around the Raspberry Pi, the battery pack, and solar panel, which are on the top of the casing. So right here, the CubeSat is making different orbits in the pre-hurricane state, and after we'll destroy the buildings, which are modeled by chess pieces and Legos, and that will simulate the post-hurricane state.
Okay, so these are the results. So the model we used to perform our image detection was YOLO V8, and our classes we used were intact road, intact building, damage building, intact car, and a damaged car. So these are the objects that we identified when we were doing our image detection. So the main problem we faced was getting enough data. Since we only got about 30 images to train the model with, and that's far too less for a model to make accurate predictions. So as you can see in our PR curve, our values are very low. And all of our classes had like very low predictions. So but we did manage to set up our CubeSat prototype and our environment as shown.
So some of the problems or lessons that we learned is that a main problem that we faced was like the time management. We just underestimated the time it would take to collect data and train an AI model, and this resulted in very poor predictions. And another thing was finding model resources, as it was hard for us to find an AI model that we could completely train with our requirements. And we also struggle a little bit with the CAD modeling, just like figuring out where every piece is placed and placing it at its certain location.
In order to scale this to a flight spacecraft, we probably need to have more data that's collected over months to make more accurate predictions. We also need a custom model which allow for more accurate predictions and would be tuned to specific parameters for detecting flood damage and hurricane damage. The solar panels will also need to be more efficient and would actually need to extend the usage of the battery, which is used in a normal function CubeSat. And the cameras will also need to be more powerful for the data, for the like proper pictures to be sent to the to the ground station.
So these are some reference that we use. We use to build a CubeSat course, Raspberry Pi forums, and we also use YouTube. Thank you for listening.